So in this video, I'm just going to try to go through the code really quick in less than 7 minutes so you can get an idea what's going on. So I'll start out with these defines, the 7seg one, which is assigned to port D. Basically, port D is going to hold, it's going to be wired to each segment of every anode on the 7-segment display. So for example, each 7-segment display has an anode lettered A through G. So I'm going to hook all those A togethers. I'm going to hook all those B together, all those C together, and basically hook each letter with the other letter on the other 5 displays. Once that's done, I'll have a problem in that every time I change the value of 7seg, it's going to output that value to all of my 7-segment displays. So if I say that 7seg is equal to I don't know, 5 or something, it's going to show 5 6 times, which is nonsensical. But we'll solve that problem by using the cathode system on because my LEDs are a cathode, common cathode, which I think work really well as far as logic goes. The anode ones are pretty confusing, but anyway. The concept behind this is that if the cathode pin on the 7-segment display is grounded, that means that the LEDs are allowed to light up. So I have a series of pins on port B that are wired to one cathode from each of the 6 7-segment displays. And we'll see how that works a little later. Define switches is basic setting up switch stuff. I'll have 2 switches that we'll talk more about in a minute. Volatile, for my variables, I had to set that. Otherwise, if I just did like int hour or whatever, or character, anything that I did, I couldn't change it outside of the main function unless I added volatile. And yeah, after I did that, everything seemed to work okay. Just declaring the function here, segment converter. This function basically translates the digits to a 7-segment representation, and it's more of a mapping, like a manual mapping that you do, because how it's mapped out depends entirely on how you wired your things. So it can be kind of messy depending on how you did it. So the point is that it's not some universal thing. Like there's no like standard, this is how you convert, digits to 7 segments. It just depends on your own setup. Okay, so we have the timer compare interrupt here. This will trigger after my timer, which I will show you later, goes off. So I have the timer set to interrupt every 1 second, and when it does, it just increases seconds. When seconds reach 60, it increases minutes. When minutes increase 60, it increases hours. And it's common sense. That's stuff that a clock would need to do in order to just work. So going down to my main function, these first few ones are just common sense. Just setting the things that I need as output, the things that I need as input. Okay, so this coming down here to this OCR1A, this is a register that my timer will use to compare the counter that it has. So once the counter reaches that amount, it'll reset so that I can keep doing my timing thing. So 1000, I figured this out through an equation. It's pretty simple math, and it's in there in the rest of the comments, so I'm not gonna go over it. But based on that equation, the number that I got was 1000, and once my counter reaches 1000, that is about a second. It's pretty accurate, so I've read that it's impossible to get it like really, really accurate with these chips, but it's close enough. Okay, so moving down, we're setting up our the WGM 12-bit here for TCC R1B. It enables the clear timer on compare. So that's what I was saying. Once the timer, the thing that it's being compared to, once the timer reaches that, which is the value in OCR1A, that can clear the timer. This one, it just enables an interrupt once a match is made. So once this is matched, or in other words, every second, bam, an interrupt is set up. And these are just my pre-scaler settings. Again, I figured these out just using the equation from the book. And yeah, it's pretty standard. It's pretty standard. Okay, so this is the part of the code that checks for the switches. I have the first switch on the 6th pin, so that's hence the logic here. I shift 5 times, so I'm at that pin, and then I compare it to the pins on the pin values for that particular port. If they match, well, that means that the switch is connected. Well, not that the switch is connected, but rather that the switch is grounded. So, and since the switch is grounded, it'll increase time by 1 minute. And below here, it'll increase time by 1 hour. So just depending on which switch you press. So here's a little bit more of the conversion process. So since I can't give 7seg a decimal value, I have to convert it first. So that's where this function comes in. And the way that it does it is, whatever my value is, I mod it by 10 to get 1 digit, and then I divide it by 10 to get the other digit. It'll always work out because the maximum value is 2 digits for all of these variables. The cathode port just tells which port to display things on. So for example, the first digit of hour is going to get displayed on the leftmost 7 segment. The second digit will be on the second leftmost 7 segment, and etc. So yeah, this is, it's just splitting a number up in 2 so that I can send it to each separate 7 segment displays. Going down further, this is the segment converter function, and it's case by case, because again, this isn't like universal. This all of these numbers are because I pinned it up a certain way. Now I did it pretty common sense wise. I try to set my pins up in order. I could have made it crazier, and it can get confusing, but I don't know. You just map it out and kind of write it down, and it works out. So yeah, just zero in my particular setup, 0 is equal to this. So once this stuff is lit up, I will see a 0. Okay, so I send the value that I need back up here. It splits it, and it tells it which 7 segment display to go to, which I kind of already explained, but just wanted to make that clear. And that is pretty much all of the code.